Hello, my name is Robert Strandh, and welcome to this series of presentations called Creating a Common Lisp Implementation. It'll be a series of presentations, but I don't know exactly how many, and this is going to be part one. So the purpose of this series of presentations is to tell you how one could create an implementation of Common Lisp using several different strategies. And in order to understand a little bit about the complications of creating such a Common Lisp implementation, I will first discuss how a compiler for a traditional batch language is created, and then discuss the differences between that and the creation of a Common Lisp system. So a compiler for a traditional batch language is a fairly simple thing. It takes an input file and runs the compiler and produces an output file. And it has a compilation environment that's initially empty. Into this environment, the compiler will enter things like macros and declarations, implicit or explicit, of functions. And when I say simple, I don't mean it's easy to write such a compiler, because there's lots of optimization passes that need to be written. But system itself is fairly simple. It has an input file, an output file, and some data structures that it will consult during compilation. So to summarize the characteristics, there are macros and declarations, and I don't make the difference here between the C preprocessor and the compiler itself. So macros and declarations are entered into the environment, and the compiler uses the environment to emit warnings and perhaps to determine how to generate code, given that a declaration might determine exactly how the code for a function call is generated. Now, if we look at the runtime support for traditional batch language, we create executable programs, and those executable programs communicate with the operating system kernel, which is the runtime support for this code. Each executable program in such a system executes in a separate address space. So system calls are used for things like file I/O, communication between programs, configuration, etc. So even communication between those different executable programs must pass through the kernel, because there needs to be a context switch in order to pass the contents of those pipes, which is sequences of bytes, from one program to another program. And this mechanism is fairly slow because it requires context switches, and it's also very primitive in that all you can pass is a sequence of bytes. So let me remind you that the initial idea of Unix was to split up programs into separate executable files, and to have those separate programs called, I guess, modules would communicate using pipes. Of course, this, like I said, this way of communicating is very primitive. So if you look at every non-trivial program, Unix program today, it does not use this mechanism to communicate between modules. Now, if we look at how a Common Lisp file compiler works, it's a little bit different. I'm using the file compiler as an example. There is also a function compile. I'm not going to discuss that function further. So the Common Lisp file compiler, it also takes an input file and produces an output file. The output file here is called a FASL file, for fast loading file. The file compiler manages a compilation environment that is very similar to the one used by batch language, in that it contains definitions and declarations maintained by the compiler. For example, if the compiler sees a defun expression, it doesn't actually create the function at compile time, but it makes a note in the compilation environment that it has seen this defun form, and it might register the lambda list for so that it remembers it later when a call to this function is compiled. The evaluation environment is something that doesn't exist in a batch language, simply because the file compiler is able to execute arbitrary Common Lisp code at compile time. When it sees an eval when with the situation compile top level, it will execute the body of the eval when at compile time, and the result of the execution is entered into the evaluation environment. Finally, the startup environment is the environment of the entire Common Lisp system that was used in order to start the compilation, start up the file compiler. The startup environment contains all of Common Lisp plus the code that you already loaded in separate libraries. So the file compiler interrogates all these environments in order: the compilation environment, the evaluation environment, the startup environment. So that's quite different from a file compiler because for a traditional batch language, because for a traditional batch language there's not this startup environment, and of course a traditional batch language cannot execute code at compile time. So what distinguishes the file compiler for Common Lisp from that of a batch language is that it requires an existing Common Lisp implementation, at least a partial one, whereas a compiler for a batch language requires no such thing, and that it may execute arbitrary Common Lisp code at compile time. Now, if we look at the runtime support for Common Lisp functions, it's the Common Lisp system itself, and those functions can call each other directly without intervention. By directly, I mean without intervention of some kind of kernel. So if we look at the characteristics of the runtime support for Common Lisp, all functions share a common address space. There's not the separate address space that you have for batch languages. And functions call each other without kernel intervention. And as a result of the common address space, you can pass arbitrary data structures as arguments between functions. You're not restricted to sequences of bytes in the form of pipes. So if we want to create a Common Lisp implementation, we need to figure out the exact differences between a traditional batch language and Common Lisp. So again, a compiler for a traditional language is a simple file translator. It has a data structure called a compilation environment, but that's a fairly simple thing, and it doesn't need any startup environment. And the runtime support for a traditional language is provided by the operating system kernel. A compiler for Common Lisp is a little bit more involved in that it can evaluate things at compile time, and it needs a startup environment. And the runtime support for the Common Lisp compiler is the Common Lisp system. So if we create a Common Lisp implementation, we need to write a compiler, of course, but we also need to create the runtime support. And creating the runtime support has some of the aspects of a traditional operating system kernel. So it's creating a Common Lisp implementation is significantly more complicated than creating a compiler for a batch language. Now, for this series of talks, I'm going to make a number of general assumptions. The first assumption is that we are creating a Common Lisp system, presumably because we think Common Lisp is a good language to write code in. So we would like to use Common Lisp as much as possible for the implementation of the Common Lisp system. We would like the resulting system to be not too slow, but in this series we're not going to talk about extreme speed either. So not too slow, but not extreme performance. The third assumption is that we're going to assume that we are creating a pre-ANSI Common Lisp implementation. At least this will be our initial assumption. So there are no classes and no generic functions. And in later parts, we might revisit this assumption to see what we can do about C-loss. So the main subject of this part 1 is a strategy that I will call Strategy 1. And it consists of writing a small core, a Common Lisp implementation core written in C, for instance in C. So the strategy is to write a minimal subset of Common Lisp in some existing language. And then we add more functionality in the form of modules. And these modules should be written in Common Lisp then, so as to write as much code as possible in Common Lisp. So we need to figure out exactly what to put in the core, what kind of functionality we need in the core in order to be able to load additional modules written in Common Lisp. Well, we need a memory manager and a garbage collector. I'm going to discuss each of these points in detail in a minute, so this is just a list of them. We need code for managing the dynamic runtime environment. We need allocators, predicates, and accessors for built-in data types. We need basic arithmetic functions for fixed nums and floating point numbers. We need a reader. We need to be able to read the additional Common Lisp code to be loaded into the system. And we need to be able to evaluate that code. So we need some kind of evaluators that can take the Common Lisp source code and execute it. And we need a version of the Common Lisp print function. So if you're writing this in C, the memory management and the garbage collection could be done as follows. We use the C malloc function to allocate Common Lisp objects. And we use the Bohm-Demers-Weiser conservative garbage collector to reclaim memory of dead objects. This is a fairly reasonable strategy. It's been used by several existing Common Lisp implementations, and it works quite well. The dynamic runtime environment of Common Lisp consists of bindings for special variables, tags for catch to be used by throw, exit points defined by tag body and block, entries for unwind, protect, and signal handlers and restarts. We could do it we could implement the dynamic runtime environment in the simplest possible way by allocating the entries on the heap as a linked list of entries. So we would have an entry type for bindings of special variables, an entry type for catch tags, one for exit points, and one for unwind, protect. We could simplify this a little bit because catch and throw can be implemented using block and return from. It's a well-known technique. It's also well known that the entire condition system can be implemented in a completely portable way using special variables. So we can simplify the number of entry types that we need. One thing we do need in the core, though, is to be able to unwind the stack. We need to be able to abandon part of the stack when something like throw, go, or return from is executed. And this functionality can be implemented using the C functions setJump and longjump. Like I said, we need allocators, predicates, and accessors for all the built-in data types. So here is a partial list of the built-in data types. And for each one, we need to determine how it is represented. And for the types that are allocated on the heap, we need to define an allocator, like make symbol, or how to create a complex number, or make package, or cons, and other functions that allocate instances of these built-in data types. We need a predicate for each one to say whether an object is of that type or not, and that predicate is written according to the unique representation that we chose. And finally, we need accessors. So for instance, the accessors for symbol would be at least symbol package and symbol name. And the accessors for constants would be car encoder and replacand or replacd. And all these functions need to be defined in the core so that we can use them in additional modules loaded later. The Common Lisp reader is a very complicated module, and it's best written in Common Lisp. But of course, in this strategy 1, we cannot write it in Common Lisp because we need to be able to read Common Lisp code for the additional modules to enter into the system. So there are two possible options that I can see. Either we write a subset of the reader in C, which is capable of reading additional source code, but not much more. And then later we replace it with a full reader written in Common Lisp. We can then, of course, read the code of the full reader using the subset reader written in C. Or we can write the final reader in C, but we can leave out complicated standard reader macros that can be written in Common Lisp later. So for instance, we might not need the reader macros for creating arrays initially. The printer is basically the same, basically has the same issues as the reader, and I'm not going to discuss it further. So for the evaluator, there are 3 possible implementations. We'll discuss each one a little bit more in detail. We can write a direct interpreter written in C. We can write a compiler generating native machine code, or we can write a compiler generating byte codes and have it combined with a bytecode interpreter written in C. So the direct interpreter is relatively simple to write. It's also relatively slow. And I'm saying here cross-evaluation is not possible. Let me explain that a little bit further. If we write a compiler, we can have the compiler execute on a separate host Common Lisp implementation, which will then generate code in the form of a file. And we can then load the file into the system that we're creating. This is something I'm going to discuss in later parts of the presentation. However, a direct interpreter, we cannot do that. It has to execute in our own Common Lisp implementation. So this cross-evaluation is not possible. We cannot execute our direct interpreter in a separate Common Lisp implementation. We can write a compiler generating native code. It's kind of hard to write, and it requires knowledge of the C ABI for the following reason. The functions that the code that this compiler will generate needs to be compatible with the C code written in the core. So it needs to respect the calling conventions of C. And we need to know those calling conventions in order to be compatible with a core functionality. And it makes tail call optimization somewhat difficult if that's what we want, because the C ABI does not allow for tail call optimization. And the final possibility for the evaluator is a compiler that generates bytecode. So it's relatively simple to write, it's reasonably fast, and we can do tail call optimizations relatively easy because we are in complete control of the ABI here. So this is the choice we're going to make, at least for the time being. We might revisit it later. And we're not going to discuss the evaluator any further in part 1, so it's going to be in later parts. So now, let me remind you that strategy 1 was to write a small core in an existing language like C. And it will be a small subset of Common Lisp. And then the strategy is to load further modules written in Common Lisp on top of this basic set. So the first complication with the strategy, and the complication is not due to the fact that it's written in a different language. The complication is due to the fact that we have an order that we need to respect between the modules being loaded. So the first complication is that Common Lisp does not have a unique set of basic operators. So there are many possible choices for the basic set. And I'm not going to discuss all the issues in detail because Henry Baker made a very long and interesting list of possible choices. And he has ways of emulating Common Lisp operators using other Common Lisp operators, and he has a fairly long list of those. So there are more complications. So let me illustrate one of the complications by an example that we would like to, say, implement mapcar in Common Lisp. And this is again a complication due to the ordering of the modules. So here's a reasonable looking implementation of a mapcar, except that it's simplified in that it uses only a single list instead of an arbitrary number of lists. So we're iterating over the list using do, the do macro, and there are two lexical variables introduced, sublist and result. Sublist is going to hold successive cooters of the initial list, and the result is going to hold the result of the mapcar function, but initially in the reverse order. So when the sublist is empty, we return the under reverse of the result because we're finished. And in each iteration, we call the function using funcall on the first element of the current sublist, and we push the result of that funcall onto our result, which is held in this lexical variable with that name, result. So this looks quite reasonable. But of course, in order for this implementation to work, the do macro must exist. And the macro expander for do may very well use mapcar to extract the local variables. The local variables here are sublist and result, and there can be an arbitrary number of those. So it would be quite reasonable to use mapcar on the list of these clauses to extract the local variables. And that's in fact exactly what SBCL does in its implementation of the do macro. So now we have a circular dependency in that we need a do macro to write mapcar, and in order to write the do macro, we need the mapcar function. So how do we solve this problem? Well, there are several different possibilities. We can write mapcar in the implementation language of the core. So in this case, C. But of course, this solution is contrary to our goal to use Common Lisp as much as possible. We'd hope to write mapcar in Common Lisp. We could use a simpler iteration construct. We could use do list perhaps instead of do, hoping that the expansion of do list doesn't require mapcar. We could use recursion, perhaps tail recursion, so that we don't need iteration at all. Or another way of not needing iteration at all is we can implement it using tag body on Go. Of course, each of these solutions is resulting in what I call unnatural code. So we would like for our code to be natural looking Common Lisp code. Of course, each of these solutions has a problem that it's not natural looking Common Lisp code. The first one is not Common Lisp code at all. The second one might not be the best way of writing the code for mapcar, so it's looking strange. Certainly using recursion or tag body and go directly is not the best implementation of mapcar. So this complication now happens for almost all the non-trivial functions that need to be implemented. For each one we need to make a decision. How do we write it? Do we write it in Common Lisp? Does it need some other Common Lisp functionality? If the dependency is circular, we need to break it somehow, and so forth. So we need a very strict order between the modules, and for each module we need to determine exactly what subset of the language is allowed to we are allowed to use at that point. And worse, during maintenance, these choices have to be known so as to avoid violations of the constraints. Imagine that you pick up a Common Lisp implementation written using strategy 1, and you look at some code and you say, well, mapcar, there's a much better way of writing mapcar. Let me write it in this more natural looking way. And by doing that, you have now violated the order between the modules, because the subset that you're allowed to use wasn't documented correctly. So as an example of how this circular dependency can be solved, I chose the implementation ECL, which uses strategy 1. So ECL defines mapcar in C. Actually, it's a C with a lot of C macros, and they use extension .d for their files. The file is called mapfun.d. It also defines other mapping functions, namely mapc, maplist, mapl, mapcan, and mapcon. This file has 170 lines of this C code. And I did the following. I executed sort mapfun.d pipe unique pipe wc-l to figure out how many unique lines of code there were. And there were 60 unique lines of code. So 2/3 of the lines of code in this file were duplicates. So not only do we have C code, which is contrary to our goals of having as much Common Lisp code as possible, the C code has lots of duplication. Now, I don't know for a fact that it was written this way in order to break this circular dependency between modules. It could be written like that for speed. So another major complication of strategy 1 is how and when do we define the macro def macro? The macro expander for def macro is quite complicated. In particular, to parse and generate code for the macro lambda list, because the macro lambda list is very complex. And to parse the body of a def macro, it's traditionally done by a function called parse macro. And if you look in the book Common Lisp the Language, 2nd edition, in fact, that function is exactly defined in there, though it didn't make it to the ANSI standard. Well, since the macro expander for def macro is quite complicated, it is very likely that it needs other macros. So in fact, if I looked at the ECL definition of the macro def macro, I found at least the following macros being used by it: setf, multiple value bind, case, cond, push, when, unless, do list, and do times. So if we need all these other macros, setf, multiple value bind, in order to define def macro, clearly we cannot write those macros using def macro. So we must use some other kind of technique to write those macros. So I looked at how it's done in ECL, and in fact many of those macros are defined using a mechanism similar to setf macro function. It's not called exactly that, but it's the same kind of functionality. So what it does is you essentially create the macro expander explicitly as a lambda, and you assign it as a macro function, uses this setf macro function. So these macros obviously cannot use parse macro, or as it's called expand def macro in ECL, but it's essentially the same thing. So instead, the lambda lists of those macros are parsed with special purpose code. So again, we end up with Common Lisp code that's not natural, and we end up with lots of duplicated code. The natural way of defining these macros would be to use the macro def macro, but we don't have that at the point that we need to define them. So that pretty much concludes part one. And to summarize the complications of this strategy, which is, I repeat, we create a small core defined in a different language like C, and we want to add modules to it, and we want the modules to be written in Common Lisp. But in fact, there are many complications. We end up with a lot more C code than we would like to, despite our best intentions. We may end up with several versions of the same module, like if we have a simplified C version of the reader and then load a complete Common Lisp version of it. We have two versions of the reader now. And much of the Common Lisp code is not written in the most natural way. It looks strange, and the reason it looks strange is not necessarily very well documented. And there are many often implicit dependencies between the modules. And the resulting system is hard to maintain, and especially hard to maintain if these dependencies are implicit. So I hope this part one has been interesting to you. And in part two, I think I will discuss the evaluator in greater detail, but I haven't made a final decision yet. So if you found this presentation interesting, I hope you will join me in part two. A date for part two has also not been set yet, but it will be announced by Fee. So I'll see you then.